Hey everybody, so these videos are here for you to watch and hopefully be able to understand the material a little bit better than just trying to read a textbook or work problems on your own. A lot of these videos we will work problems, a lot of them I will be kind of breaking down the major topics. If you notice here, we're starting in chapter 1.4. That's because I feel like, you know what, you could probably figure out 1.1, 1.2, 1.3 all on your own. So some of the chapters will go through every topic. Some of them we're going to kind of like pare it down. These should be relatively brief videos so that you're not having to sit there and listen to me drag on for 3 hours or anything like that. All right, so let's get started here in measurements in chemistry. All right, in measurements in chemistry, right, first off, we need to talk about our different measurements, right? And so measurements have a few different things that are associated with them. Number one, there's going to be a number. We should all be kind of familiar with what a number is. I could tell you the number is 1.23. Okay, great, right? You understand what the number part of it is. I don't want yellow. All right, so that tells us something, right? That tells us some sort of a value, but it doesn't tell us everything. Next up, we also need to have some sort of a unit that is associated with it. Right, 1.23, well, 1.23 what? Okay, well, that could be 1.23, and so that could be 1.23, say, meters, right? Or it could be 1.23 kilometers. Those are two vastly different things. And so we have to say what those are. So let's say that those were 1.23 meters, right? Then we would also include that in there. And then lastly, there has to be, we talk about some sort of uncertainty associated with a value, right? And so almost all of our values that we're going to come across in a chemistry course are going to have some sort of uncertainty to them, right? And so when we talk about 1.23 meters, what we're talking about is the fact that, right, we're probably pretty sure that it's close to 1.23, but it could be 1.23, say 1 meter, or it could be like 1.229 meters. It's somewhere in that range. And so sometimes we have to, give what that uncertainty is by saying that it's plus or minus some value, right? And here I'm just putting in 0.01, right? But we include our uncertainty there when we report that measurement. So those are the three parts of a measurement that we're going to have to kind of go through. All right, so first off is our units, right? A lot of times our units are really easy. They're things that we've probably heard of, things like, meters. Now, we don't necessarily use meters all that often here in the United States. A lot of times, we use feet and, yards and stuff like that. But the rest of the world, they use meters, and we probably have come across those. Seconds, maybe even grams of things, right? Those are some of the units that we've probably heard of. Those are like our base normal units. Right, well, then we also have some other units that we call derived units, right? And derived units are where we've got combined units. And those are just things like, hey, if you've got the volume of something, that might be meters cubed, which is meters times meters times meters, as it's shown down here, right? Or the density of something. The density of something, notice, has two different units in it. It's grams over liters there, right? Density could also be in grams over milliliters or some other units, but it's got the multiple units that are in them, and those are things that we call derived units. All right, so next up, let's talk about the mathematical treatment of these measurements as we go along. Okay, so, right, again, we're going to come back to that idea of the uncertainty in our numbers, right? So some things don't have any uncertainty. Not very many things, but some of them do, right? Like if we want to count things, right? If I gave you 11 pennies, right, well, that's easy for you to count. 1, 2, 3, 4. You can count to 11 most likely, right, if you made it this far in your life. So, right, there's 11 pennies. That's an exact number of pennies. It's not like you've got maybe 8 pennies and maybe 13 pennies. You have exactly 11 pennies. So that's an exact number. There's also things like defined conversions. Okay, like let's go with, the American units. right? We could say that there are 3 feet in 1 yard. Okay, those are exact values, right? There's exactly 3 feet in a yard. It's a defined amount, right? Or if we go to what the rest of the world uses, right, we could say that there might be, say, 1,000 meters in 1 kilometer. Okay, there's exactly 1,000 meters in a kilometer. That's what's defined by it. Now, pretty much everything else that we come across, though, right, there's going to be some sort of an uncertainty to it, right? And so we're going to have to take that into consideration, right? There's some sort of a limitation into how we estimate things. And this comes down to also when we are measuring things along the way. Right, let's say that I wanted to measure something that was this long here. Okay, what I mean by there being some sort of an uncertainty here is that, okay, this gradation here is a 1. So we know it's at least 1. Okay, and then it's going to be point. And then we're going to count 1, 2, 3. Okay, so it's at least 1.3. Okay, but notice that where it ends, right, that is somewhere in between 1.3 and 1.4. And so we have to make some sort of an estimation on, what we think that is. And so in this case, it's probably somewhere around 1.35. But that last number is uncertain, okay, because we had to make some sort of an estimate there in order to report that value. And all of the values that we're going to come across that we deal with in a lab setting or that are reported to us in word problems or something like that, they are usually going to come with some sort of an uncertainty unless it is a specifically counted thing or there is some sort of a defined conversion that's along with it as well. Right, so that's where those uncertainties come from. All right, so when we deal with this, then we have to talk about what numbers that are reported are significant. Okay, so here when we report our answers, right, we're always going to report our answers to the correct number of significant figures, including some sort of uncertainty that was involved in it. All right, so we had that number from the previous slide of 1.35. Okay, well, that value, right, has 3 numbers associated with it, 1, a 3, and a 5. Okay, all of those numbers, when we talk about them, are significant, even though that last one, even though that last value is estimated, it's still a significant value to us because it's telling us something about what's going on there. It's telling us that we don't know that it's exactly 1.3, that it was somewhere between 1.3 and 1.4. So we need to include it. It is significant there. So whenever you report anything in class or in lab, you have to also include your uncertainty in order to give off all the information to your readers or the people that are looking over your work. Okay, so how do we determine if we're given some values, which values are significant and which ones aren't? Okay, so if you're given a bunch of numbers, right, number one, like we've got the number there, the 3090, right, and notice that it's got what I call a captive 0 and a trailing 0. And I'm bringing those up right now so that we can kind of talk about what those mean here in a minute. And then also I've got that number of 0.008020, right? And I've got some leading zeros. I've got a captive 0 and a trailing 0 there as well, right? So I'm bringing all of those up so that we can see once we actually count which values are significant or not, what I'm talking about, right? Captive zeros are in between non-zero values. Trailing come after non-zero values. Leading come before non-zero values. Okay, so significant figures. All right, certain numbers are always significant, right? Any non-zero values are always significant. Okay, so the numbers 1, 2, 3, 4, 5, etc. Those are always significant. So if you see those in a reported value, right, we have to report those as being significant. Any of those captive zeros that are in between other, non-zero values, those count as being significant as well. Any trailing zeros, if they are to the right of a decimal place, then they are going to be significant as well. Okay, so right when I'm talking about that, my non-zero values, right, are things like the 5 and the 6 there, right? My captive zeros, I don't have any of those. My trailing zeros in this case, right, I've got a trailing zero in here. All right, this has 3 significant figures to it. All right, now we might be looking at it and you might be like, okay, well, what about those zeros that were out in front, those leading zeros, right? Leading zeros are not significant. Okay, and you might be like, well, why are those not significant? And that's because we can write that same number and we can write it in scientific notation. We can write it like this, and that tells us the exact same information there. Okay, and those leading zeros, they don't really tell us any of the actual information. All they are a placeholder. And so they aren't technically significant. So when we're counting things up, right, we want to make sure that we can count the right number of significant figures for things. So in this case, the leading zeros on anything aren't significant. Same idea if I've got the number 4044. All right, it has 3 non-zero digits, and it has a captive. Oops. Right, and it's got a captive one as well. All right, so right, this has 4 significant figures. The same idea though is like, right, I mean, this number here, you don't ever write numbers like that, right? That's why those leading zeros don't mean anything and they're not significant. All right, now, trailing zeros, when they're to the left of the decimal place, also aren't significant as well. Okay, so those zeros there really aren't significant, and so we don't like to write numbers like this, and so we're not going to come across this. Much because like really those zeros are very ambiguous. They don't tell us a lot of information. They're confusing, and so we're probably going to like not really deal with those very often. We're going to try to ignore them as much as possible. I'm probably going to not have them be part of our stuff that we come across as problems throughout the semester here. Okay, so when we've got these significant figures, why are they important for calculations? Well, we need to be able to use them to report our answers to the right number of significant figures in the end. So when we add or subtract answers, they should be to the fewest number of decimal places. Okay, so I'm going to show as my example 10.134 plus 2.2. Okay, so right, what I want to do when I've got a problem like this, right, is I'm going to report my answer to the least number of decimal places. Okay, so the answer to this would be 12.334. Okay, but that's not the right answer to the right number of significant figures. So in order to do these, when I'm doing addition and subtraction, I like to line them up like I would do if I was working this in the second grade. Right, 10.134 and 2.2. That way, I can kind of write a line here that shows where my significant figures end, right? They end with the one with the least number of decimal places, which is only one decimal place. So my actual answer then, right, is 12.3. My actual answer is going to have 3 significant figures, right? Notice that the first number, 10.134, has 5 sig figs, and the second one has 2 sig figs, 2.2. But my answer has 3. So we can't really figure them out from those, right? What we have to do is we actually have to solve it in order to get there. When we multiply or divide something, all right, when we do that, we have to report our answer to the one with the smallest significant figures. All right, so what I mean by that is we're going to look at okay. All right, if I have, I don't like this. I'm trying to do it on the fly here, and I'm not liking what I'm doing on the fly. So I'm gonna erase it real quick here. Let's do a new one here. Let's do the one we've got up there, 10.134. All right, divided by 2.2. Okay, so the answer to this would be 4.606363636. Okay. All right, if I put it in the calculator, I'm going to get that ridiculous looking answer there. Okay, but, right, what is this to the correct number of significant figures? All right, I'm going to put a 0 in here just so that I make this a little bit different than the one above. So again, I'm kind of going on the fly, which I don't really like to do. I should have written one out, but there we are. Okay, so this number, the 10.134, has 5 significant figures, and the 2.20 has 3 significant figures. Okay, so we want to report our answer to the one with the smallest number of significant figures. So you got 5 and you got 3. Well, 3 is smaller than 5, so our answer should be the 3 significant figures. Okay, so our answer is 4.6, so that's 2 significant figures, and then we need one more number in there, and so we got 4.60, oh, but it's 0.6, right? So we're going to round up. So the answer is 4.61, because it needs to be the 3 significant figures, and we use our old school rounding rules. 5 and above there, we're going to round up. 4 and below, we would round down. All right, let's move on to chapter 1.6, which are some more measurements in chemistry here. All right, and so here we're going to be talking about something that we call dimensional analysis. All right, and I'm just going to point out that this is the crux of chemistry. If we can do dimensional analysis, that's what every problem really boils down to. It's being able to look at the units of things and being able to solve problems. All right, we're going to do some easy ones here, which has no chemistry whatsoever, and then we're going to start doing chemistry ones in the future chapters. But that's what really chemistry is doing this thing that we call dimensional analysis. Okay, and this is relating the amounts of things to their different units. And what I mean by that is by converting from one unit to another unit. That's really what chemistry is all about. Okay, so if we can do this, then we are going to be way ahead of the game. So we should be practicing these things as much as we possibly can, early and often. Okay, so we're going to work a couple of sample problems on the next slide. Right, but what I want us to note here, whenever I've got it kind of laid out, right, is let's look at something like this guy right here. Okay, on here, I want us to kind of understand how to read this. And so what this is really saying here is that kilo is 1,000. Okay, what that really means is that the number of base units, all right, which is right here. So I'm kind of comparing these two yellow areas. Okay, that the number of base units, so this really is telling us that there are 1,000 base units equals 1 kilo unit. All right, so all of these are kind of based on like the base unit. So what that's also saying here is, like, what if I wanted to compare like these two? So like centa. All right, so right, if I wanted to do like what are like centimeters. Okay, so what that means is that there's 0.1 base unit, which are meters, is equal to 1 of the centa units. Okay, so it's always 1. It's always 1 of these guys here is equal to however many of these of the base units. All right, sounds confusing. I get that it's kind of confusing, but I'm hoping that when we see it, we'll be like, okay, I can do this. All right, so come back to this, work problems with it, do a lot of sample example problems, and hopefully we'll get these down. So let's see a couple of sample problems here. I've got 1.23 kilometers, and we want to convert that into millimeters. Okay, so as I said on the previous slide, there's 1,000 base units, so meters, are equal to 1 of the kilometers. And if we were to look at that slide, there's 0.001 base units are equal to 1 of our millimeter units. All right, so now what we want to do is we're going to figure out how can I use these to convert from one thing to another. Okay, and so when you have two numbers that are equal, okay, like I've got up there, my 1,000 meters is equal to 1 kilometer. Okay, they can be written as ratios, and we can write them as ratios to use as conversion factors. And what I mean by that is I could write this as 1,000 meters per 1 kilometer, or 1 kilometer per 1,000 meters. All right, we're going to see that, of why that's useful here. Okay, so let's see. I'm going to start with that 1.23 kilometers. All right, now I have kilometers in one place here, right there. So I want to get rid of kilometers. And the way that I get rid of units is by dividing them. Okay, so like if I took kilometers times kilometers, that would be kilometers squared. But kilometers divided by kilometers, they cancel each other out. So if I put the kilometers here on the bottom, I'm dividing by them. And I'm going to put my meters on the top here. Okay, so my kilometers have canceled out. And so what this is really telling me is I'm taking my 1.23 and multiplying it by 1,000, and I'm dividing by 1. All right, now I'm not at millimeters yet, but I have my other conversion factor out there, my 0.001 meters and my 1 millimeter. All right, and so if I look at that, right, my meters cancel there. So look, the units that I'm left with are millimeters. Those are the units that we wanted. All right, so now we would do this. So we're going to take our 1.23 multiplied by 1,000 multiplied by 1. Okay, and then we're going to take that and we're going to divide by all of the things on the bottom. So divided by 1 and then divided by 0.001 as well. And we're going to get 1.23, and that's times 10 to the 6th millimeters. Okay, so that's how we do these dimensional analysis problems. All right, now then for our next one, right, I have my 0.023 centigrams to milligrams. All right, this is a little bit tougher because there's no base units here. But if you look on there, right, note that the centigrams, right, if we were able to go back, which I can't seem to do, is be able to scroll back, but centa on there is 10 to the minus second. And milli on there is 10 to the minus third. So centa is 10 times bigger than a milligram is. Or another way of saying that is that 1 centigram is equal to 10 milligrams. Okay, I've got two numbers that are equal to each other, right? So I can write them as a ratio in order to do a conversion, all right? And so, oops, these are grams, centigrams. Okay, so I'm going to put the centigram on the bottom, 1 centigram on the bottom. I'm going to put those 10 milligrams on the top. Right, those centigrams go away, and we're left with our milligrams. All right, and I have 0.23 milligrams then as my answer. So again, work a lot of these, because if we can get them down with the base units of just, distances, time, grams, stuff like that, if we can get the basics of those, then once we get to the chemistry, then they should be relatively straightforward for us to go through there. All right, the other thing that we got out of this chapter is just doing temperature conversions. All right, so in the United States, temperature is usually given in Fahrenheit. All right, basically nowhere else in the entire world is temperature given in Fahrenheit except for the other, big powerhouse called Burma. Everybody else uses Celsius, right? Well, as a scientist, though, we use kelvins. Okay, and so pretty much everything that we do, we're going to have to convert into kelvins. All right, so I've got some different conversion factors down here. And hopefully these then just become, hey, let's plug things in and chug from there. So if you wanted, say, if you want Fahrenheit and have Celsius, you would use this. Right, if you want Celsius and you have Fahrenheit, you'd use this. You want Kelvin, have Celsius, we're going to use this. You want Celsius, you have Kelvin, you're going to use that one. All right, so pretty straightforward, hopefully. Like, you're just kind of then, we're not doing big conversions, we're just plugging and chugging as these things go. All right, so let's see, right? We're going to have a nice day, at least as far as I'm concerned, that is 73 degrees Fahrenheit to Celsius and Kelvin. All right, so, right, if we want to do our Celsius one, right, our degrees Celsius is equal to our degrees Fahrenheit minus 32 times 5/9. Okay, so our degrees Celsius is, all right, 73.0 minus 32 times 5/9. All right, is 22.8 degrees Celsius. All right, now notice that I have written this as 3 significant figures because we started with a value, 73.0, that had 3 significant figures, and then everything else in here is actually an exact number. We are exactly subtracting off 32, and we're exactly multiplying it by 5/9. Those are part of the equation, and so we're going to assume that those are exact values. Okay, now if I want to get Kelvin, Kelvins are equal to our degrees Celsius plus 273.15. All right, so we have our 22.8 plus 273.15, which is 295.95. All right, but again, 273.15 is exact value, so we really need to report this to 3 significant figures. So that would be 296 kelvins there. All right, so that concludes our very first chapter. All right, so hopefully you'll be able to get some use out of these as we go along, and I'll see you once we start chapter 2.